Hey everyone, this is Dr. Walker. In this video, I'm going to go over example of 570, number 1. The problem says that we have a loop of wire hanging vertically, it's carrying a current, and it's immersed in a vertical uniform magnetic field. I have drawn the loop here. I have drawn it as viewed from the front with the 4 sides and the current going counterclockwise. And then the loop is also drawn here as viewed from side number 3, where side number 4 is on top, so the current is going into the page where side number 4 is, corresponding to this side right here. So the problem says that the loop can rotate around side number 4, so we're going to consider this a fixed point. What angle does the plane of the loop make with the vertical? So you might be thinking, well, if it's rotating, wouldn't the angle keep changing, right? But what's going to happen is that it's actually going to make a specific angle when it's in static equilibrium, because it's going to be rotating one way due to the magnetic field, but then it's going to be rotating the other way due to the gravitational force. Let's take a look at those rotations. We know that if the current is going into the page here and out of the page at the bottom, then we can curl our fingers in the direction of the current, and that means that your knuckles are pointing away from you, your fingertips are pointing towards you, your thumb is pointing to the left. That's the direction of the magnetic moment that has been drawn here. And the magnetic field is upward, and we know that the magnetic moment wants to align with the magnetic field, so the loop is going to rotate clockwise. So once the loop is at an angle, you can see, I've redrawn it again here. Once the loop is at an angle, then you know that the weight here, which acts straight down at the center of gravity, that's going to produce a rotation counterclockwise. So there's going to be a specific angle theta, which is this angle right here, which has been drawn here. A specific angle theta for which the two torques are going to be balanced, and that's what we're trying to figure out. So we're going to start the problem by saying that the sum of the torques is equal to 0, and we want to find the two torques. First, the torque due to the magnetic force, which is mu cross B. Remember that torque has a direction, so let's find the direction of this torque. We're going to use right-hand rule number 1, right? The cross product is putting your fingers in the direction of the first vector and then folding in the direction of the second vector, which would be folding upwards, and you'll see that your thumb is pointing into the page. So into the page, if we look at this coordinate system, that's going to be the negative z direction or negative k direction. So the cross product is going to be negative mu b sine of phi, and there's going to be a k direction here. So the reason I call this phi is because phi is the angle between mu and b, which I will label right here as phi. But we want to find theta, so we want to go ahead and rewrite this in terms of theta. Notice that theta is the smaller angle here, which is the same angle right here. If we want to find the sine of phi, or which is the same thing as finding the component of B here, that is going to be perpendicular to the magnetic moment, right? Be perpendicular to magnetic moment, that's sine of phi, the opposite side. That side is adjacent to theta. So we can say that sine of phi is cosine of theta. That way everything is in terms of theta. So there we have it, the torque due to the magnetic force. And now we want to find the torque due to the gravitational force. So we can write it as a cross product of R cross F sub G, where R is the vector that points from the pivot point to that force. That's our R vector here. But we know that this is equal to RF sine of theta, where it's equivalent to finding the component of the force that is perpendicular to the object being rotated. So we're trying to find F perpendicular here, which is going to be opposite of theta, right? If we draw theta right here, you can see that F perpendicular is opposite. So we can rewrite R cross F as R F sine of theta, and let's not forget a direction. If we do the cross product, you put your fingers in the direction of R, which is down and diagonal to the left, and you fold them downward. Your thumb should be pointing towards you, which is the positive z direction, so positive k direction. So the last thing we can do is we can write R is a distance from the pivot to where that force is acting, and that distance is half of that side, and that side had a length b, so R is equal to b over 2. So now we are ready to sum up our torques, set them equal to 0, and solve for the unknown theta. We're going to have negative mu b cosine theta k direction plus b over 2 f sine theta k direction equal to 0. So go ahead and move the first term to the other side. We're going to have little b over 2 f sine theta. We can cancel out the k's here, is equal to mu b cosine of theta. Now we can go ahead and divide by f here, divide by b, and multiply by 2. So divide by b and f, multiply by 2. And let's also divide by mu b here. Oops, no, I didn't mean to do that. Let's divide by cosine of theta to bring that over here. So that's going to give us sine of theta over cosine of theta, which is tangent of theta, is equal to 2 mu b over little b f. And we could have made the substitution earlier, right? This f sub g here is the weight, which is mg. So making the substitution at the last minute here for the weight. And so now we just need to solve for theta, plug in all of the values. So the angle is going to be the inverse tan of 2, and we need mu, right? Mu is NIA, so N was 1. I forgot to make that substitution. Actually, let me go ahead and make the substitution here, and then we won't have to plug all the numbers in, but I'll show you what the numbers are. So remember, mu is NIA. N is the number of loops, which is 1. I is the current, which is given. And A is the area of the loop, which is the length times the width, which is little a times little b. And we'll see that the little b actually cancels out. Okay, so now we're ready to find theta, and I'll let you plug in all the numbers, so I don't have to plug them in, but I'll tell you what they are. We have 2 times I, which is 3.5 amps, times little a, which is 0.2 meters, divided by m, which is 50 grams, converted to kilograms. So just divide it by 1,000. And then g, which is 9.8. So plug all of those values in, and you will get theta is equal to 1.64 degrees. So I just wanted to go over this example so we could practice working with the definition of mu cross b to find a torque, and it also brought in some Physics 1 concepts such as static equilibrium, which are always fun problems to solve.